Hello everybody. Today in this new session, we are going to discuss about the hypothalamo-pituitary axis. In our previous lecture tutorial in hypothalamus, we observed that in the hypothalamus structure, there is a important structure, bulky structure is known as the tuber cynarium, then followed by infundibular will come down. From there, anterior pituitary will produce, then posterior pituitary, again it will come up, and again another bulging is there, which is known as the mammillary body. Now, in this hypothalamic segment, there is a segment we mentioned is known as the supraoptic zone. So supraoptic zone is the first segment here, and another zone in this area is known as the tuberal zone. I think you remember this thing. So this is the tuberal zone. Now, what happens in these two zones? The supraoptic zone consists of two important nucleus which is related to this hypothalamo-pituitary axis, which is known as the supraoptic nuclei and the paraventricular nuclei. So this is the supraoptic nuclei and this one is the paraventricular nuclei. From there, the neurohypophyseal tract will come down and it will reach into the posterior pituitary zone, which is known as the neurohypophysis. So this is the posterior pituitary, or known as the neurohypophysis. Okay, and from the neurohypophysis, the most important hormones that are released from the posterior pituitary is known as the ADH or vasopressin and the oxytocin. We will discuss all these things in this lecture. Oxytocin. And the tuberal zone will have important big nucleus, which is known as the arcuate nucleus. Now here I would like to mention that both the supraoptic and paraventricular nucleus, there is important cell body from which actually the neurophysin and the pre-pro hormones of the ADH and oxytocin will be produced, which is known as the magnocellular neuron. So magnocellular neurons are present, or cell bodies are present within the supraoptic and paraventricular nuclei, and the arcuate nucleus, which is known as the arcuate nucleus. I hope you remember this thing. Arcuate nucleus present in the tuberal zone, and in this zone or in this nucleus, the important neuron that is present is known as the parvicellular neuron. And this parvicellular neurons is the main structure in the arcuate nucleus, where from the different releasing factors will produce, and subsequently they will come down through the tuberohypophyseal tract. Then it will produce the primary capillary. From there, it will again produce the secondary capillary network and reach into the adenohypophysis or the anterior pituitary. So this area is known as the adenohypophysis, or the, we can say it is the anterior pituitary area, and here it is the posterior pituitary. Now this primary vessels is known as the tuberohypophyseal tract. It is known as the tuberohypophyseal tract. What is it? Tuberohypophyseal tract. From there, it will produce what it is known as the hypothalamo hypophyseal portal system. Why it is portal system? Because there are two sets of capillary network. One is the primary capillary network, and here is the secondary capillary. It is the primary capillary network, and here is the secondary capillary network. And from the secondary capillary network in the anterior pituitary or the adenohypophysis, there are several trough cells are there. At least five types of trough cells you must know. That is the corticotrope, thyrotrope, lactotrope, somatotrope, and gonadotrope. We will discuss all these things in this lecture subsequently. So from these tropes, there are this releasing hormone or releasing factor help to produce several types of hormones, and ultimately these hormones are coming out from this anterior pituitary and come into the circulatory system and produce cellular action. So this is the overall basic funda regarding the hypothalamo pituitary axis. Now we shall start our discussion from which side, that is from the neurohypophysis or the neurohypophyseal hypothalamo neurohypophyseal tract, by which ultimately ADH and oxytocin will produce, and how they will actually produce and what are their action or role in our body, that we first discuss in our next slide. So for this thing we must know the normal osmolarity of our body is around 270 to 290 milliosmol per kg H2O. So this is the normal osmolarity or osmolality, whatever you can say, in our body. And outside the blood-brain barrier, outside the blood-brain barrier, we have osmoreceptors. What are those osmoreceptors? One is the organum vacuolosum of lamina terminalis, and one is the subfornical organ. Again, it is the organum vacuolosum of lamina terminalis. It is the main osmoreceptor or osmoregulator which can sense our osmolarity in our body fluid. Okay, and this is known as the subfornical organ. Though they are present in the central nervous system, but they are actually present outside the blood-brain barrier. Subfornical organ, and they basically stimulate by increase the angiotensin 2, mainly the subfornical organ actually stimulated by the increased angiotensin 2 level in our blood or body, which actually produced by the renin angiotensin aldosterone system. By the action of the renin angiotensin aldosterone system, there will be production of the angiotensin 2, and which ultimately trigger our osmolarity when there is increased osmolarity or decreased blood volume in our body. Now osmoreceptor or osmoregulator can sense change in osmolarity as low as less than 1% to maximum 2 to 3% milliosmol per kg H2O, and in change blood volume as low as 10 to 15%. That means these receptors or osmoregulators can change in or say can sense the change in the osmolality when there will be increase the osmolality even as low as less than 1%. These two organ can sense this thing, as well as if there is decrease in the blood volume at around 10 to 15%, then also this two organ can sense this thing, and immediately what they can do, this osmoregulator, after sensing as minimum increase in the osmolality less increase in the osmolarity as low as less than 1%, or decrease in the total body water by blood volume at least 10 to 15%, this thirst center and osmo organum vacuolosum of lamina terminalis actually stimulate the magnocellular cells of the supraoptic and paraventricular nucleus of the hypothalamus. So first, what happens when there will be change in the osmolality or change in the blood volume? They actually stimulate which site of the hypothalamus? They actually stimulate the magnocellular cell, M cells, present in the supraoptic nucleus and the paraventricular nucleus in the hypothalamus. Which site? At the supraoptic zone. Okay. So after stimulation of this supraoptic and hypothalamus and paraventricular nucleus of the hypothalamus, the synthesis of ADH and oxytocin process will start. Now, this magnocellular neuron will do what? They are actually present in the short arm of chromosome 20. So these are present in the 20p chromosome. These magnocellular neurons are basically present in the 20p chromosome. They are first doing what? Transcription. So transcription, as we know, the central dogma process of the protein synthesis. Transcription, then they will produce mRNA, and from there heteronuclear RNA will produce, and this heteronuclear RNA will do what? They will first produce three structures here. One is the exon A, exon B, and exon C. Now, in between this, there is the intron. They are the introns. So exon A, exon B, and exon C connected with the introns, and after the splicing process, this intron will separate and they will produce mature RNA. This mature RNA is known as the exon A, exon B, and exon C. Exon A, exon B, and exon C. Now, after production of this exon A, B, and C, they are undergoing translation. So they are undergoing translation, and this translation process will produce pre-pro hormones. One is the pre-pro oxytocin and pre-pro vasopressin. So transcription will lead to produce pre-pro oxytocin and pre-pro vasopressin. Within this pre-pro oxytocin, there is another co-secreted peptide is there, which is known as the neurophysin. So this neurophysin within the pre-pro oxytocin is known as the neurophysin or NP2, and here the co-secreted peptide neurophysin is known as the neurophysin 1. Here you need to understand this thing. So after translation, there will be production of pre-pro hormones. One is the pre-pro oxytocin and one is the pre-pro vasopressin. Along with this, there is another segment which is attached with the pre-pro oxytocin is known as the neurophysin or NP2, and here in the pre-pro vasopressin, one structure is there which is known as the neurophysin 1, and from there they will produce pro hormones. So pro oxytocin and pro vasopressin. Okay, in the Golgi body complex, they are present in the Golgi body complex, packed in the Golgi body complex, and the structures will be like that. One side is there is the amino terminal, then AVP or the vasopressin we can say, then there is a neurophysin 1 for the vasopressin and neurophysin 2 for the oxytocin, and one is the glycoprotein. All these things, and last segment is the Kuch segment or the acid segment. So they are present in which area? In the Golgi body complex. Golgi body complex. And from there, they are released as vesicle packed with the pro hormones that are pro-oxytocin and pro-vasopressin. So they are released and packed in the vesicles, packed within the vesicles. And these vesicles, when they will reach into the axon terminal, this is known as the herring bodies. So herring bodies are what? Herring bodies. Most of the time this MCQ can be asked in the examination, various competitive examination, that what is herring body? This herring body is nothing but the packed vesicles present in the axon terminals, in which has actually the pro-hormones like pro-oxytocin or pro-vasopressin along with the neurophysin 1 and neurophysin 2. And what happens? They will actually descending down via the microtubules and the molecular motor kinesin towards nerve terminal at posterior pituitary lowermost part called the pars nervosa. So these herring bodies are basically descending down at the nerve terminal, in which part of the posterior pituitary is known as the pars, at the pars nervosa, at pars nervosa of the posterior pituitary. Okay, now this is known as the orthograde transmission, the first transmission via the kinesin molecular motor, and the speed is around 400 millimeter per day. These herring bodies are actually descending down by the orthograde transmission by the molecular motor kinesin, and this speed is the 400 millimeter per day. At the nerve terminal, it is constructed as 4 tetramer of the neurophysin 1 surrounded by 5 subunits of vasopressin, like that. And the structures at this nerve terminal is like that. It is the structure of the oxytocin, pro-oxytocin or pro-vasopressin, whatever you can say. And 4 tetrameric subunits are there, like in this fashion. And what structures are present basically within this area? Here it is the, at the center, the structure is the either oxytocin or the vasopressin. And here is the neurophysin 1, again for the ADH or vasopressin, I hope you can remember, and neurophysin 2 for the oxytocin. Here it is the neurophysin 1 for the vasopressin, actually I am drawing here, neurophysin 1 and neurophysin 1. These are the 4 tetrameric subunits, and 5 polymers are there in the outerwards side. So ABP denotes the vasopressin or the ADH prohormones. Okay, so they are present along with the glycoprotein subunits. They are present along with the glycoprotein subunits. And finally, what happens? They actually cleavage to form separately vasopressin or the ADH, whatever you can say, ADH, then neurophysin 1 and the glycoprotein. Subsequently, this neurophysin 1 and the glycoprotein subunits will be inactive, remain dormant state in the circulation, and this ADH as well as the oxytocin, ADH from this structure, and if it is their neurophysin 2, then oxytocin also, they will come into the circulation. So ADH and oxytocin will come into the circulation. So that's the process by which the magnocellular cell actually help to synthesis the ADH and the oxytocin from the pars nervosa of the posterior pituitary by the action of the hypothalamo neurohypophyseal tract. And what are their function? Now this vasopressin, when it will come into the circulation, they actually work, vasopressin will work on the vasopressin 1A receptor, vasopressin 1A receptors in the blood vessels, and they will actually vasoconstrict the blood vessels, and also it actually normalize our blood pressure. And this vasopressin can also act on the vasopressin 1B receptor, and vasopressin 1B receptor is actually present in the anterior pituitary, from which by the action of this vasopressin ACTH can be released. So ACTH can be released indirectly by the action of the vasopressin also from the anterior pituitary gland. On the other hand, if this subunit is the ADH, this ADH will act mainly in the collecting duct of the nephron at the late part of the collecting duct. If it is a nephron structure grossly, and finally it will come into the collecting duct. At the late part of the collecting duct, it is present there at the apical site. What is present at the apical site? There is a receptor, V2 receptor is present. This V2 receptor will be activated when there is increased ADH concentration, and this V2 receptor is actually the G protein coupled receptor, and has action similar with the G stimulatory alpha. Now G stimulatory alpha ultimately phosphorylate the protein kinase A. This protein kinase A ultimately help to synthesis the channel which is known as the aquaporin 2 channel, and this aquaporin 2 channel ultimately attached at the apical site at the collecting duct, late part of the collecting duct, apical site, by the action of the microtubule, and this aquaporin 2 channel will attach tag at the apical site, and from there they are actually help to reuptake of the water from the collecting duct, or reabsorption of the water will take place by the aquaporin 2 channel from the apical site, and this water will come into the medullary interstitium by the action of the help of the aquaporin 3 and 4. So aquaporin 3 and 4 channels are present at the basolateral site, of the collecting duct. So collecting duct basolateral site help to reabsorb the water from the tubular lumen and into the medullary interstitium. So by this way, our blood volume or the extracellular fluid volume will be normalized, as well as osmolarity of the body fluid will also be regulated, and it also help in the regulation of the blood pressure. On the other hand, if there is production of the oxytocin is there, so oxytocin, what is the different function of this oxytocin? It actually help in the milk ejection process. Milk ejection during the lactation period, milk ejection will occur, or it helps in the mammogenesis. Growth in the mammary gland can also be helped by this oxytocin. So mammogenesis will be done by this oxytocin. Number one, it also help, how it can help in the milk ejection, which is known as the milk ejection reflex. What is that milk ejection reflex? Let's talk about that ejection reflex. How it will start when baby suckling the mother's nipple. So suckling stimulation will lead to generation of the action potential, and this action potential will traverse by the thoracic T4, T5 and T6 afferent nerves, and subsequently they will come into the hypothalamus. At which part of the hypothalamus? At the magnocellular cell present in the supraoptic nuclei and the paraventricular nuclei of the hypothalamus, from where by the action of the neurohypophyseal tract, oxytocin will produce, as we have discussed this thing previously. So oxytocin will come into the circulation, and this oxytocin will work on the myoepithelial cell. So myoepithelial cell are present in the breast gland, and by the action of the G protein, as this oxytocin will work on the oxytocin receptor, which are actually the G protein coupled receptor and has action similar with the GQ. So GQ mediated action will lead to increase in the calcium ion influx, and this calcium ion actually help in the contraction of the myoepithelial cell. So myoepithelial cell will be contracted. Myoepithelial cells will be contracted. So contraction of the myoepithelial cell will lead to ejection of the milk. So milk ejection will occur. So this is all about our milk ejection reflex, which is done by the oxytocin. On the other hand, what is the other action of the oxytocin? It is actually help during the parturition or the expulsion of fetus from the uterus during labor. So parturition, how it will possible? During the pregnancy, last stage of the pregnancy or third trimester of the pregnancy, there will be abundant number or the increased number of the oxytocin receptor in the uterus. So oxytocin receptor present in the uterus. So when there will be release of the oxytocin, it will work on the oxytocin receptor, which are actually G protein coupled receptor and has action similar with the GQ. So whenever there will be GQ mediated action, there will be phosphorylation of the protein kinase C and the inositol triphosphate synthesis. Both of these actually increase the calcium ion concentration. So part of the calcium ion will be there in the uterus, and it actually increase the myometrial contraction. Uterine cell is known as the myometrium, so myometrial contraction. Here it is the myometrial contraction occur. Myometrial contraction by the action of this increased calcium ion. And finally, there will be the cervical dilatation and expulsion of the fetus from the mother's womb. So expulsion of fetus will occur. This is known as the parturition. Oxytocin also help in the mental well-being. This is the second action. Third one is the oxytocin also help in the mental well-being. So mental well-being can be maintained by this oxytocin. Number 4, important, and the recent research shows that oxytocin may help to build long-lasting love. So oxytocin may help to build long-lasting love and maintain loyalty to the partner. Long-lasting love. That's why it is also known as the loving hormone. So researcher actually named this hormone loving hormone due to its nature of action. So this is all about our hypothalamo neurohypophyseal tract and the hormones that are released from the posterior pituitary and their action. Now